we continue our discussion on the k nearest neighbor classification technique. So, let me explain it with a small example. I have the previous training set table. So, where I have examples of different species. So, my training instances are each of these species. Okay, so, I have them and I have to put them into one of two classes, mammals or non-mammals. And each of the training example is described by a set of 4 attributes, say give birth, no, live in water, you can fly, live in water and have legs. So, 4 attributes. So, for example, say a whale is described by 4 attributes, give birth yes, can fly no, live in water yes and have legs no. So, this is the 4 dimensional vector of some attributes describing the species whale. So, similarly, I have so many species described and my classification task is the following. Suppose I have a new species whose attribute vector is like this, it gives birth, it does not fly, it lives in water, it have legs and I have to predict what is the class of this new species, mammal or non-mammal. And we have repeated this exercise previously for the base classifier. Now, we will do it for the nearest neighbor k nearest neighbor classifier. So, I will use a k nearest neighbor. So, the first thing you need to do is to choose a value of k, how many neighbors to take. Well, so there is no real theory to say what should be the value of k. So, we go by this. So, let us see how many examples are there. So, my n number of examples equals 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 examples. Okay. So, what is my k? So, one of the thumb rule is k equal to n by 10, so which gives me 2. Okay, but I really do not want k to be 2, I would rather want k to be an odd number, let us say 3, the nearest odd number, because if there are 2 classes, if I choose k equal to 3 and if I vote between the classes, there will not be any tie, one of the class will be the winner if I have odd number of k. I could have chosen another strategy, maybe I could have chosen k equal to root over 20, root over n. So, which would give me k to be around say 5. Okay. So, up to me. So, I really do not know what is the right value of k. So, let me do for k equal to 3. Let me do for k equal to 3. The next thing I need to consider is what is my distance function. So, that means, if I have 2 4 dimensional attribute vector or feature vector representing 2 species Okay, I have not drawn it properly. So, let me see. I have taken this species a bat, I am taking another species an owl, and based on this 4 sized vector, how do I define the distance between these two species? In other words, what is my distance function? Okay, so there are many possibilities. One thing is that probably Euclidean distance will not hold here, because they are not continuous valued. They are Euclidean distance you can define when there are points in some real space. Okay, but I have discrete values here. So, what is a possibility? So, let me see, bat is yes, this is bat, yes and yes and no, attribute values I am writing down, and owl is no, owl is no, then yes, then no, then yes. Okay. So, how do I define how close these two vectors are? Again, there are many possibilities. One possibility, let me see, is that I just count so rather okay. So, I just count how many attributes have same value. So, okay, not this, not the give birth, can fly, yes. So, 1 here, 0 here, this is also same, this is also same. So, distance between bat and owl I can write it as 3, okay, I can write as 3. Okay. So, similarly, let me check what is the distance between bat and a whale. So, whale, let me write down. So, it whale is yes and then no and then yes then no. So, this distance between these two is 3. Now, let me see what is the distance between these two vectors. So, 1 here, 0 here, 0 here, 0 here. So, distance is 1. So, you can see the bat and owl, sorry, maybe you might have found out a mistake that I have made. This 3 is not really a distance, it is kind of inverse distance, it is the similarity, not the dissimilarity. Okay, it is the inverse system. So, maybe I can define my distance to be not 3, but not 3 and 1, but maybe 1 by 3 and 1 by 1. Okay. So, as you can guess that bat and whale are more far apart, they have more distance between them than bat and owl. Okay, so this is just an example. So, I can this is I can use some other distance also. I can use some other form of distance also, right. Yeah, so, when you actually apply it, it will depend on your domain. It will depend on your domain. Okay, so let me continue with our example. So, what we will do is that I will take, I call this as x, this new example. This is this vector. No, and once I have defined my distance, I have defined my distance, I can use that function to find the distance of x, not this point, with each and every member of the training set. Each and every member of the training set, I find my distance. So, if I call these training instances as maybe Z1, Z2, Z3 and so on. So, there are up to Z20, and if I define D as my distance between x and certain Z, Z1 let us say. So, I will have 20 such distance values, where distance I have already defined. Okay, I will have, sorry, this is 2, this is 3. So, dot 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 up to dx with Z20, each and every training instance. So, actually if your training site is size is large, this is going to be computationally expensive. Okay. So, next what we do, if you remember, what I do, I sort these distances, these 20 distances in ascending order, smallest distance first. I sort this distance in ascending order and find the top 3 training instances, top 3 Z's that are closest to x. So, top k rather, Z is a training point. Okay. So, top k in terms of closeness to x that we are trying to classify. So, every time you classify you try to classify a point, you have to find all these distances. Okay. So, what are the top distances? Let us see. So, yes, no, yes, no, yes, well, closest. Any other yes, no, yes, no? Yes, a dolphin is the second neighbor. So, this is the closest neighbor, this is the second closest neighbor. I have taken k equal to 3. So, I have to find one more close neighbor. So, both these have distance equal to 0. Okay. So, what is the third closest neighbor? Find out. So, yes, all these are matching, no, all these are matching, and then yes, no, dolphin, yes, no, yes, no, this is not, yes, no, yes, no, yes, no, this is not. So, maybe a human, check the human, yes. So, this has d equal to 1 by 1, okay, d equal to 1 by 1. So, 1 is the number of mismatch, 1 by 1 is the inverse of that is the distance. So, this is the third neighbor. So, this x has 3 neighbors that we find out, k equal to 3. they are a whale, a dolphin. See, I may make mistake. I am a old person. I can make mistake, but you don't make a mistake. And human. I am just illustrating, so it's not really a problem if I make the mistake. So fine. So these are the three neighbors. Let me write it properly. I cannot write a bad handwriting though. And these are the three neighbors of X. What are their class membership? So whale is a mammal, dolphin is also a mammal, and human is a mammal. So if you take a vote among these two class, mammal, non-mammal, definitely this is going to win the vote. So X, class of X, I take it to be mammal. If you go back to the lectures on Bayesian, Naive Bayesian classifier, you see Naive Bayes also classified it as a mammal. Okay. So I think it is clear to you what we did. We just follow these steps. It's simple. I mean, in fact, if you write a small program to do this, it will be only a few line program. You have to find distance and find the top case, sort them. Okay. But if you have worked out these steps and maybe written a program, you will find that there are some expensive computational steps involved. The first expensive step is the computational time for a new point, which I will call a query point, sorry, which I will call a query point. You have to find its distance to all the training set n. So in other case n was 20. So this is expensive if n is large. Okay. So there are two possibilities, three possibilities rather. You find out you use a data structure which we will discuss to quickly find this distance. You can use an approximate distance and you can reduce n, the training set. Reducing this n also reduces the memory requirement of storing the training set. Okay. Of course, you have the. So, anybody you can you just tell me, answer this question. What is the complexity of the KNN classifier? This is an important question. So, let us see. So, if each takes d time, the okay. So, you have understood this question. So, what we want to do is that I have an n-training example and it is a d dimensional data. So, finding distance between one pair of point takes d time, capital D proportional to capital D time. What is the complexity of giving the class, inferring the class? Gives order of n distances, order of n distance computation, and each of them takes d time. Okay. Takes, so you have to sort them to find top k. So, it will take order k n, finding top k takes order k n time into n into d. So, it is linear in k, linear in dimension d, and quadratic in training set size. Okay. So, you can imagine as d becomes more and n becomes more, it takes more time. Okay. All right. In fact, you have to choose your k depending on d also. All right. So, what let us try to do is to reduce my n, reduce the training set size n. There are, as I have mentioned, there are two options: either you reduce training set size, a process known as condensing, or use some better data structure for fast search. We will discuss these two. Let us see how to reduce this. So, as we had discussed, I can have a Voronoi cell for each of the training points. I am explaining for one n, it will hold for general k. And if you take all the blue class points and union their Voronoi cells, you get the class boundary. Okay. You get the class boundary. So, now if you reduce your these points, remove some of these points and keep only few, your Voronoi cells will become larger. Okay. But if it is so that even with these large cells, the boundary is intact, it does not change. then that smaller set of points is sufficient. Okay. So, you that is what I have written, you just read it once. Okay. So, it is kind of sufficient to have only this many. So, I will describe an algorithm which does this. There are actually two ways of doing it. One is boundary is remaining same, another is what is the minimum set which preserves the boundary, MCS, minimum consistent set. Okay. So, this is the picture. So, I describe an algorithm to do this. Describe an algorithm to do this. So, what I do is that following. So, this is my initial training set. So, Z1, Z2 training points. Make a smaller bin. Randomly pick up k points from here and put them here. Okay. Now, with this small set of points, try to classify the points here. The points that are misclassified, if a point is misclassified, you transfer it, increase the size of this set. Again use that to classify this. Repeat this until there is no transfer. Okay. So, you read the steps. So, you have to transfer till there is no more transfer, and this small set no longer of size k, it will be larger than k, is the condensed training set. Okay. I will use now this condensed set for my KNN and I will throw away this big set. Since it is smaller size, computational complexity will also decrease. All right. So, this is the idea. So, there are many other related algorithms, I am just explained one of them. So, with this I close this lecture on this nearest neighbor. In the next lecture, I will discuss those data structures for search in high dimension. Thank you. I will just continue in my next lecture on the high dimensional data structures for geometric data structures. Thank you.